Minerals are the building blocks of the Earth, but did you know that minerals themselves are commonly made of shared building blocks? We can visualize the crystal structures of these minerals using a series of 3D printed building blocks called TotBlocks. In this video, we'll explore the crystal structure of the Palygorskite Group. Palygorskite is named after its type locality, Palygorskaya, in Russia, where it was first discovered in 1862.
Members of the Palygorskite Group include Palygorskite, Euphortiarite, and Wind Mountainite.
This is the crystal structure of the Palygorskite Group, which consists of double-chain width TOT modules, which are connected by palysepal type linkages.
Now we'll take it apart. To learn how to build the component TOT modules of this structure, take a look at the assembly of TotBlocks video in this series.
To construct the Palygorskite structure, connect one double-chain width TOT module to a second double-chain width TOT module, such that the T- module of the first is joined to the T+ of the second. A third double-chain width TOT module can then be joined such that the T+ of the first module is joined to the T- of the third module. This pattern can then be repeated as needed to extend the structure. Here, a fourth TOT module is added to the second and third TOT modules to complete the structure and to highlight the channel spaces between the TOT modules.
The crystal structure of Palygorskite contains large channels that are typically occupied by water. However, other molecules can be trapped in this space. For example, the pigment Maya blue is notable for its longevity. Its vibrant tones have been found in Mesoamerican pottery dating back to the 10th century AD. How has this pigment resisted a millennium of degradation? Well, the Mayans mixed indigo with Palygorskite, and the indigo molecules were trapped in the mineral's channel spaces, which prevented the color from degrading. In the crystal structure of the Palygorskite group minerals, the T sites are dominantly occupied by silicon, whereas the M sites in the O modules are occupied by magnesium, aluminum, ferric iron, and some in vacancies. There's also a site called the M4 site that borders the O module, but it's usually vacant. The channel spaces are mostly occupied by water molecules. In this video, we've learned about the crystal structure of the Palygorskite group. The palysepal type linkage of the TOT modules creates large channels in the structure, which can be occupied by water and other molecules.